A photon emitted during the de-excitation of electron from a state n to the first excited state in hydrogen atom irradiates a metallic cathode of work function 2 electron volt in a photocell with a stopping potential of 0.55 volt. Obtain the value of the quantum number of the state n. Now see what's the question saying. The electron is de-excited from some higher energy level to first excited state. First excited state means n is equal to 2. This is ground state, third, fourth, and so on. So from some higher energy state n, it has de-excited to the first excited state. Now we know that whenever there is de-excitation, a photon is emitted. The energy of the photon is given by the difference of the energy levels associated with the excited states. That means En minus E2. This is Bohr's postulate, right? Now this photon is also incident on this metallic cathode, which has work function 2 electron volt and stopping potential 0.55 electron volt. That means the photoelectric effect is taking place. Now by Einstein's photoelectric emission, photoelectric equation, H nu is equal to H nu naught plus EV naught. Work function plus kinetic energy. Work function is given to you. Stopping potential given hai, so we can find out the kinetic energy in terms of electron volt, which will be 0.55 electron volt. So equate these two and find out the value of n. You know what is the energy? What is the energy of the electron in nth state? We have done this formula. It is minus 13.6 by n square electron volt. We have done this for hydrogen. This is the energy of electron in the nth excited state. So use this formula and find out the value of n. Let us see the solution here. So this is photoelectric equation, Einstein's equation. H nu is equal to phi naught plus EV naught, 2 plus 0.55. Now energy in the nth excited state. This is the formula for hydrogen. For the first excited state, that means n is equal to 2. Put n equal to 2 here. We get minus 3.4 electron volt. Energy difference, subtract the two energies. You will get this and then equate this with this equation. Equate these two and you will get n equal to 4. Okay, next is determine the distance of closest approach when alpha particle of kinetic energy 4.5 mega electron volt strikes nucleus of Z80, stops and reverses its direction. So this is the alpha particle. This is the nucleus of Z80. Distance of closest approach means that entire kinetic energy is converted into electrostatic potential energy at this point. Therefore, it turns back, it stops and it turns back, it traces its path. So, the kinetic energy is given to you, it's 4.5 mega electron volt. 4.5 mega electron volt equated with potential energy. This is the kinetic energy. It is equal to the potential energy between the alpha particle and this nucleus. So 1 by 4 pi epsilon naught Q1 Q2 by R. Q1 is 2E for helium for alpha particle and Q2 is ZE for nucleus upon R naught. Put all the values and you can find R naught from here. Don't forget to convert 4.5 mega electron volt into joules. 4.5 into 10 raised to power 6 to convert into electron volt and then multiply with this value to convert into joules. Spectral series of hydrogen atom. Now we know that whenever electron jumps from higher energy level to the lower energy level, there is radiation emitted of certain frequency or certain wavelength. That radiation is called spectral line. That is called spectral line. For example, when the electron is de-excited from this level to this level, a wavelength of this much value is emitted. From this level to this level, this wavelength is emitted. So these all are spectral lines. Now we know this. This is Bohr's postulate. Whenever electron jumps from certain orbit Ni to Nf, this is initial orbit, this is the final orbit, such that Ni is greater than Nf means it has come from higher orbit to lower orbit. Suppose N is 4 to N is to orbit 1. So higher to lower orbit, energy will be emitted, radiation will be emitted of frequency nu, and this h nu is equal to Ei minus Ef. We already know this. Now we know the formula for energy of electron in a particular state n. We have derived this. We find out the formula of energy in Ni state. Replace N by Ni. So this is the energy of the electron in Ni state. This is the energy of the electron in Nf state. Now put both the values in this equation and you get this. Take this thing common, 1 by 4 pi epsilon naught square, 2 pi square, Me4 pi h square. This is all common, and this will be in the bracket, 1 by Ni square minus 1 by Nf square. The next step is take this negative sign inside the bracket. So it will become 1 by Nf square minus 1 by Ni square. Next, what I'm doing, I'm bringing this h here. So this is the frequency of the emitted photon. It is equal to this value, h cube हो जाएगा यहाँ पे. Okay, and then from here I can find out the wavelength of the emitted photon. जब transition हुआ तो जो wavelength emit हुआ वो हम find कर सकते हैं. Replace nu by c by lambda. Frequency is c by lambda. Now next step, what I'm doing is I'm bringing this c here, this c here. So 1 by lambda is this value. Now this whole thing is a constant. You can see that everything is a constant. This is called Rydberg's constant. This is called Rydberg's constant. And the value of Rydberg's constant for hydrogen atom is this. You have to remember this value. The unit is meter inverse, of course, because this is 1 by lambda. 1 by lambda is called wave number. So the formula is this. You can directly use this formula. So this is giving what? This is giving the wavelength of the spectral line emitted. Wavelength of the spectral line emitted when electron is jumping from Ni to Nf. Final state, Nf is the final state, Ni is the initial state. Okay, now we have named the series when the transition is from some higher energy state to the first n equal to 1 state. From some higher energy state to Nf1. So this is called Lyman series. कहीं से भी second n equal to 2, n equal to 3 से n equal to 4 से जब n equal to 1 पे fall करेगा, that means ground state पे fall करेगा, that is called Lyman series. We name that spectral series to be Lyman series, and that series falls in UV region. Okay, and Balmer is what? किसी भी higher energy level से जब वो second state में, that means first excited state में when it comes, you can see from here, this is n equal to 1 ground state, n equal to 2 है. तो कहीं से भी n equal to 3 से 2 या 4 से 2 या 5 से 2 या 6 से 2, final state should be 2. This is called Balmer series, and this spectral series lie in the visible region. Then next is Paschen. Paschen में क्या होता है? Final state 3 होता है. From any higher state to final state 3. This is Paschen, and it falls in infrared. Then is bracket. Bracket is NF4. From transition is from some higher energy state to NF4, and the spectral series lie in the infrared region. P fund, it is the transition from some higher energy state to the energy state corresponding to NF5. And this also lies in infrared region. Now, we have just done this formula, wave number formula, and I have named this as RH, Rydberg's constant, this constant. तो हमने अभी ये formula किया है wave number का. Now, if I'm asked the energy of the emitted photon, वो भी हमने formula किया, but if I've asked the formula in terms of RH, ये formula भी, we have derived this formula ना, h nu is equal to this into 1 by nf square minus 1 by ni square, but मुझे अब RH की terms में चाहिए. So what I'm doing, I am multiplying this equation, this h nu equation, multiplying and dividing by hc. Multiply and divide by hc. Now this whole thing is RH. See from here, this whole thing is Rydberg's constant. So I've converted my formula. H nu is equal to RH into hc into 1 by nf square minus 1 by ni square. This is the energy of the emitted photon in terms of RH. So you may get numericals in which you have to use this formula.